Okay, let's look at it on the drawings now, the triangle array. And you can see the position, how it's not square. Looks like that, right? It looks like that, and that's where the parking is. So let's go to the wall, since that seems to be a favorite discussion of some people. Here's our wall. Over to the pool. This acts like a infinite non-deflecting surface, this wall system with a ledger into it. So I don't treat it as a column. Of course, you can have shear across it, but I don't treat it as a column so that it's no deflection. I don't treat it as a beam. So columns, of course, can buckle. They can punch through also. They have their shearing. Let's just look at it in one of the formulas. Is a 2-to-1 ratio, pretty much, that you max out. And the width of this is 19 feet. 19 feet, 19 feet, 19 feet. So it's symmetrical thereabouts, the garage area. Here, here, here. I mean, the pool deck area. 19 feet. 19 feet 6. 20 feet. 20 and 20. And so on, 20, and then, well, we're not down in the failure zone anywhere. We're here. Here's a larger 20. Here's a 19. These are the larger columns here. The larger columns are here, rather, correction. Larger columns are here. I'm looking through a camera to try to do this for you. And so they have more of a protection because they have more surface area. Now this is, so looking at that 2-to-1 ratio, it's 19 feet. So what is the height? What is the distance from here to here? It's reported as 27 feet. 27 from here to here. So it's almost, it meets the requirements. There's 19 by 27. So from this point to this point, back to the entire wall, it meets the requirement of being a two-way slab, the dimensions-wise. I know a lot of engineers don't like that dimension rule, but it exists. So now we need to consider the reinforcement. The main bars at the bottom in tension should also be going multiple directions. The main bars for these span. So then the thickness of the concrete matters. So it will hold up will help with deflection, and also punch shearing here. Now I'll give you an idea what that would look like. So on the crate, this would represent our wall. This represents our main bars. Two-way slab, I'm going to consider them both main bars. And this will be our concrete pad with reinforcement in multiple directions, plywood. Our securement are just going to be the fasteners that I staple through, holding this to the surface. This will be moved around in multiple videos for you based on allowing 10% deviation. Allowing a 10% deviation from this corner here, considering it's a ledge, even though it's cantilever right now, but from this corner lined up with the column here, just twist it a little bit, no big deal. This is within 10 degrees, that span. And that's the 2-to-1 ratio. This fits for this location to this location, and to this location is less than a 2-to-1 span. Now, I can use different things to determine degrees. I shall use a digital protractor, if you will, angle finder. And we have another column over here. So these columns are just bricks that I get to move around. So right now I've got them in line with each other, and I have the ledge. And if you take note, right under here, there's a little bit of a gap right here, just a little bit. So I'm going to load myself on top of this deck, if you will. So the ledger, the only part that's deflecting up is down at the end. The negative load, as I talked to you guys about, the negative load is it lifted off the floor there. As I step off, it touches down on the floor. Just about. Step up. That's the negative load. Because you get nothing for free. Since this creates a bow here, let me zoom out. Bow. The deck bowed. Some people looking at the other direction. Hogging. Anyway, so the deck was depressed at this location. Let's put it that way for you. Depressed at this location. I still didn't fold through, right? Because the load still transferred down through the columns. But on the other side of this column, it took a negative load, a negative direction, and went up. So a break here creates a downward force that creates a negative load up over there. But more so inside this area here where the stresses are created. Because it's the pivot point, if you will. And that's the pivot point over there, that one. So I'm not going to do it in this video, but I'm going to do put a crack inside here. I'm going to saw across. And once I saw across, you'll see that now the deflection will be greater until it's met. And I showed you this in other real models, but this in concrete. But imagine if I were to put a cut through here, a break, a fracture, that the deck will fold down, will fold inwards, until it hits the butting of the other face of the fracture. Then that will be its new resistant location, if you will, its new profile. And it will be something like that, let's call it. Say that's flat. And say I just take it up just a little bit. And then it butts the other side. The other side will butt to it. And it will do the same. And then when they butt, they'll now be in compression at the top and stop the deck from going down any further, putting a hell of a lot of stress right here for keeping the deck from deflecting down, from continuing going, is that crack location here. It's in compression. If we were able to route that out again, the deck would take another moment. And as it does that, see the negative lift up on this end going up? Well, that's not for free. It comes across the column, stressing this column head, the shear heads of it, right? We don't want that. So why the smallest cracks matter is because they're telling you where the stresses of the deck are revealing themselves, especially the underside. When you look in the garage area, you see those cracks going over. That's indicating that the deck is opening up, that the deck is sagging, and you're getting an opening. I'm lifting the side up, but the bottom is coming apart. So this is the bottom coming apart. I'm exaggerating. The top is compression, so it spalls off up top. The concrete spalls off top because the hinge point is up here in the concrete, and down here it opens up, and it looks like a nothing crack to you. But it took, to get that crack there, it took quite some movement. Just a hair crack here, movement up top, which would then create that sagging of the deck. The sagging of the deck, sorry. So as we look at these two bricks together, at the bottom they're tight, and at the top surface they're gapped. So what happened there? Well, that's what happened there. That little hogging action happened. Deflection up. That would represent itself here at column heads. You would see cracks. Shear heads, you see cracks opening up like that. If this side of the deck is going down, that side's going up. Planter box being over them, you wouldn't be able to observe them. You would not be able to observe them. This is part of the things where people say, well, it lasted 40 years, but it was unobserved pretty much for however long they had the planter boxes on top of them. So this could have been happening. And here's the interesting part, is that I went through the as-built, if you will, and that's because the engineer hired a surveyor to survey the deck. Surveying the deck, it looks beautiful. It really does. You look on one side to the other side, you may see some quick indicators of a half-inch drop. Overlay that with the drain system, and you say, okay, well, that's going towards the drain. You're just not finding that the deck has indicating itself as much. But it kind of is, because you're way out here when you all of a sudden see a quarter-inch drop in the deck. but the profiles seem to match going towards drains as I'm profiling it. Still working on that, but the point is, it's a very little bit of a deflection. Creates a huge, this little bit of deflection here creates a huge gap at the top. It would be filled at the top. This means you're already having a negative load on each side of your supports. Now, on the parking garage area, in between where the cars drive, where they park down the driveway, if you will, remember they did that in the 80s. I think they put all this urethane in it. And then they came back and did it again. But now watch what happens now we're at the parking garage area. Watch what happens now when I make that area compressive tight and I open the bottom. You see how the bottom's open? Well, I had to lift up this side over here. To do that, it was a load on top of here. And that could be the dead load span of the deck being too far from here to there for the wire reinforcement and the cycle loading. And so the rebar gets stressed along with the concrete. The stresses are there, and they allow some slippage. And when they allow that slippage, it opens up at the bottom there. And then they go and they caulk it. They put a caulk adhesives in it, etc. Epoxies. That didn't stop it. That's still going that direction. That's not the issue. They need to now pin it, if you will, lock it in so it doesn't deflect anymore, or add columns or whatever they need to do. There's the beginning of the end, and that was back in the 80s. Now, a short period after the building was stable, in other words, all the curing process took place. And no, I'm not interested in talking about concrete takes forever to cure, 100 years plus. I'm not interested in that as an argument, as a counter argument. We're talking the 28-day typical rule. So so then we have that gap down there, and that slippage is not for free because over the column heads, it's now ripping and tearing, and I showed you in a video of that. It's tearing apart the shear heads, its ability to hold the deck on top of these shear heads, and over many cycles, and including the planter boxes hiding this defect. So on this defect, it would look probably when it cracks open, it would be an open crack as we would see at the top. And then perhaps, because this is trying to profile itself through the deck, that would be profiling itself through the deck, meaning through the deck. It would look like fractures like this. And say you don't find fractures like that, all that means is that the deck is not failing. The thickness of the concrete is sufficient, and it's not causing that spidering crack, if you will. So just because you don't see that doesn't mean you're not. It just pretty much means you're sufficient, and in your thickness of your deck, that it's not failing through that compressive fracturing shear mode, which you see that crack like that. So you have this though, which now means you're now losing your marriage on top of the shear head. And so see that? Scratch myself. So then they're going opposite directions, like I showed you. They're going this way. It was supposed to be up there, tilting down, and you're getting your sagging, and those stresses are here. Now, I saw that people were trying to evaluate the flaps of the concrete and not the rebar. The rebar is what you want to evaluate, the condition of the rebar position, not the flaps of the concrete one way or another, because the flaps of the concrete that you're looking at are indicators of the overlay. And the overlay could have been put on here like this with a seam back here. So when this punches through, the overlay just lifts up. But what matters is what happened to the concrete below, because there's a seam there. Say it's a 90 here. When this goes down, it just flaps up. It could do the same this direction and flap up. Don't get confused with that thick overlay as a direction of the concrete, which way the concrete is going, because you have to take into consideration how is it jointed. How is that jointed? You know, it's over here, and it falls down. Bloop, it just lifts up. All right, or it lifts up that direction. Fractures off there. So the joints matter of the overlay. So that's not a very good indicator right now, without the data below it, of the concrete. Is what matters. How did it look? How did it look during failure? And we have found none. I have not found one image of that that they presented to us. But I used the rebar reinforcement in my video to show that which direction the deck failed. And it's kind of simple or evident that the deck pretty much had a slight deflection, put stress over the shear heads, and then puncture through. Because if the deck were to fail in one span, like right here, for example, span, it would push this column over. It would want to push the column over, or it would pin itself against the column. But it didn't. As it punched through, maybe it did pin just a little bit, and then now the new loads are face mounted here and ledge mounted over there perhaps. And the moment the stresses are on an incline up here, and it breaks at 4 foot off the wall because of all the built-in control joints, if you will. I'm using quotations on control joints. That is the planter boxes all in there, along with the 1'9", along with the other openings they put there, acting as a control joint, and including the reinforcement coming off that wall. Hopefully this was somewhat helpful, and I'll do more like this, just going to keep them short, I hope, and they'll stack. So you got to take what you see here, go over it again, and then I'll stack it here, and then I'll stack it and I'll stack it and keep going. I'll stack it and keep going. All right, take care.